thank you so much for joining me as we journey through chemistry. In this video segment, we're going to be looking at the percent yield, or sometimes called the percent efficiency of a chemical reaction. Very important in industry. And what is expected really depends on the reaction. Sometimes we're expecting 99.5% yield because there are no side reactions and it goes 100% to make product and there's no loss in the process. Other times they're happy with 5 or 10% yield just because of the nature of the reaction itself. There's not this right answer or even a correct range. Now, honestly, you can even get an experimental yield that is over 100. And that can happen if your product is contaminated. Say it's wet, you didn't get it dry all the way, or it's contaminated with unreacted reactant or that type of thing. So there's not a range I can give you for percent yields, but I will show you how we're going to calculate that. So I have methane gas, CH4, burned in oxygen. We assume complete combustion unless you're told otherwise. Incomplete combustion makes carbon monoxide. We're going to be dealing with carbon dioxide, again, unless you're told otherwise. And when you balance this is a 2, a 1, and a 2. So we have 42.00 grams of methane at STP. So we have methane gas, and it's at STP. Okay, now then it tells me that 40 grams are experimentally produced. What is the percent yield? So as soon as I see that, I like to write down my percent yield formula. And that's going to be my experimental over my theoretical. My theoretical comes from my stoichiometry calculation. Stoichiometry deals only with pure reactants, and we get theoretical or maximum values, and that's times 100. So I like to pop that down right away so that I'm not tempted to use this 40 grams. This 40 grams, they're telling me, is my experimental yield. It does not go in my stoichiometry map anywhere. So then it said, so I want to know how many grams of water. They gave me the experimental amount, I can't speak, the produced experimentally amount of water, okay? It's getting late at night on that one. All right, and so we want to go mass to moles, and then we're going to go moles to moles, moles to mass. All right, now hopefully you are pretty good at doing that by now. I'm going to do that quickly. But I want to caution you here. You notice that the question pointed out that we have a gas at STP. But you know what? We don't have a volume. We're not asked for a volume. We have grams and we're going to moles. So we never use it. It's extraneous information designed to see if you really know what you're talking about. So that's grams of methane. I want to go to moles of methane. Sorry, that line's there. I have to find a way to get rid of that. Now I want to go to moles of water. There's 2 moles of water formed for every 1 mole of methane. And then there's 18.02 grams of water for every 1 mole. So here, for this particular example, my experimental yield was 40.00 grams. But in theory, I could have made, if everything was perfect, 94.31 grams. So if I plug those numbers in and I solve for my percent yield, we would get, in this case, a value of 42.41% yield on that. Okay, there must have been loss, maybe incomplete combustion. It's hard to say. Okay, so that is percent yield. Let's try one more, and this time we're going to be solving for a different variable. So we have a reaction, combustion reaction again of octane. Combustion reactions are kind of nice because they give us a little more complicated mole ratios. So C8H18 plus 25 oxygens. I know that sounds like a high number, but that's what it is. 16 CO2 plus 18 H2O. Okay, now this time I know my percent efficiency. So I know I have 84.3%. Okay, and that's going to equal my experimental over my theoretical times 100. Now, in this case, what would I actually expect to form? What would I get in an experiment? So this is my unknown. So this is going to be my second step because I have two unknowns right now. The theoretical is what I'm going to get from my stoichiometry. So I have 95.00 grams of liquid octane, and I want to know grams of water. So we're going to go mass to moles, moles to moles. This should be something you can do in your sleep by now. Okay, and kind of running out of room. So I'm going to erase some of this here and give myself a little bit more room. Okay, so we're going to go moles to moles, moles to grams. Let's get our mole wrote up. 95 grams. I'm going to be a little fast on this one because you know how to do this by now. Mass to moles, use molar mass. And that's of our octane. And then we want to get rid of moles of our octane and go to moles of water. There's an 18 in front of the water. There's a 2 in front of the octane. And then there's 18.02 grams of water for every 1 mole of water. This gives me my theoretical. That means I get 134.88 grams is the maximum that I would produce. So we're going to pop that in there. We'd have 84.3 is our experimental yield over the theoretical that always comes from our stoichiometry times 100. So I would expect to have had an experimental yield of 114 grams. So now what a scientist would do here is kind of backtrack and figure out what I need, what can I expect to produce with a given amount. All right, so a variety of ways this would be used in industry, but a pretty important application to real life. I hope you enjoyed that. Take care.